Welcome to my channel Mathematical Clinic of Subash. We are here in the 8th lecture of permutation and combination. Today we are going to establish the formula of finding combination. We are beginning today's lecture by the theorem. Find the combination of n given objects taken all at a time. So r at a time. Here you are given with n objects. Suppose they are x1, x2, x3 up to xn. We have to fill r places, first, second, third up to r places. You have to make a combination having r component. First component, second component, third component up to rth component. This question is different than the question of permutation in the sense that if you keep x1 here and x2 here, thereafter some numericals, and consider this as one combination, one result, one arrangement, and interchange them, keep x2 here, x1 here, remaining all same. And if it is the problem of permutation, then this one will be different. This may be considered as the second arrangement one. But if it is the problem of combination, then this one is same as the last one. So these two cannot be considered as different arrangements rather than single arrangement. Now here we are in the process of combination. So there is no order in the components. No order in the components means if you interchange the position of x1 and x2, then the result so come is same as the result we have given here. We have to find how much such arrangement can be made. That's our target. Suppose x such combination can be made. First combination, second combination, third combination, xth combination. Suppose x such combination can be made. It means the answer of our question is x. Now let us consider how many components are there in each combination. Because you have filled r places. There are x object in each combination one. Suppose first one is x1, x2 up to xr. Second one may be different than this one. Third one may be different than this one. Suppose x such arrangements can be made. So we have to find the value of x. X such components have been made. Arrangements have been made. Now let us think, if we consider there is order in the components here, then how many permutation will be there? If we consider, if you just suppose that there is order in the components here, then it will be the work of permutation. Then how many permutation would be there? Actually there are n objects and n places. Sorry, r objects and r places. So p r comma r equal to factorial r permutations are there. So you can say that if we suppose that it is the work of permutation, then in one combination there are factorial r permutation. Same thing happens here. Here also there will be factorial r permutation. Here also there will be factorial r permutation. Here also there will be factorial r permutation. So altogether, how many permutations are there? If you add all of them, factorial r plus factorial r plus factorial r, how many factorial r? X times. This will be the total number of permutation present there. But the total number of permutation present there will be n given object to fill r places. Total number of permutation is pn comma r. Is it? If you take piecewise permutation there in the first combination, it is factorial r. Permutation in the second combination, it is also factorial r. Permutation there in the third combination, it is also factorial r. Permutation in the xth combination, it is also factorial r. So total number of permutations there equal to sum of all of them. But the total number of permutation there will be n given objects are places to be filled. So total number of permutation is not other than Pn comma r. Let us simplify it. Sum of x factorial r will be x multiply factorial r. Sum of 2 factorial r will be 2 multiply factorial r. 3 factorial r will be 3 multiply factorial r. So x factorial r will be x multiply factorial r. And we have the formula for this one. The formula is n factorial divided by n minus r factorial. So from here we are able to derive the formula x equal to n factorial divided by r factorial into n minus r factorial. Because x is the required number of combination. What's x? It is combination of n given objects taken at a time. So formula for the combination of n given objects taken at a time will be n factorial divided by r factorial into n minus r factorial. This is the theory we were wishing to establish. Now we are going to derive some of the remarkable formula from that major formula 1. The formula we just derived is combination of n given objects taken at a time is n factorial divided by r factorial into n minus r factorial. Let us replace r by 0. Substitute r equal to 0 here. What happens? Cn comma in place of r 0 equal to n factorial by in place of r it is 0 0 factorial, n minus r becomes n minus 0 factorial. This will be n factorial will cancel and 0 factorial is 1. That is why the result is 1. So we are able to say that in the case of combination, if second component is 0 then the value is 1, no matter what the first component is. Likewise, let us replace r by n. What happens? It becomes Cn comma n. Here also n factorial as it is. Replace r by n, it will be n factorial. Here also in place of r we substitute n, then n minus n equal to how much? 0 factorial. N factorial will cancel. Again we are left with 1. So if both the components are same, then also the value of combination becomes 1. Let us move to fourth one. Let us find the value of Cn comma n minus r. Simply apply that formula 1. First factorial, it means n factorial by second factorial. Second component's factorial means n minus r factorial into first minus second factorial. It will be n minus plus r factorial. This is exactly n factorial divided by n minus r factorial as it is. Here n cancel, it is r factorial. This is the same thing, this formula 1. In place of n factorial by r factorial into n minus r factorial, what can we place? We can place Cn comma r. So we have established another formula 1. If needed, Cn comma r be replaced by Cn comma n minus r. Move to another remark 1, number 5. If Cn comma r equal to Cn comma r dash, what happens? Let us see here. This Cn comma r as it is. Can this Cn comma r dash be written as, by this formula 1, Cn comma if r dash, then it can be written as Cn comma n as it is, and in the place of second component 1 we can replace by first minus second. First minus second will be here n minus r dash. First components are same, so second component must be same. This implies r equal to n minus r dash. From here we are able to see that. Take r dash on the left, it becomes r plus r dash equal to n. That is why we conclude that if Cn comma r equal to Cn comma r dash, then sum of second components r plus r dash must be equal to the first component 1. And we are going to establish one more formula of combination, that is called Pascal's theorem. Pascal's theorem asserts that Cn comma r plus Cn comma r dash becomes Cn plus 1 comma, sorry, it is not r dash, it is r minus 1. Then the sum of the combinations becomes Cn plus 1 comma r. Let us prove this one. Our left hand side is Cn comma r plus Cn comma r minus 1. First components are same, and here this one is the predecessor of the second component here. R, then its predecessor r minus 1 must be here. Simplify it by the basic formula of the combination. The formula for Cn comma r is n factorial divided by r factorial into n minus r factorial, plus formula for this one is n factorial divided by r minus 1 factorial into n minus, first minus second becomes n minus r minus minus plus 1 factorial. Is it? Let us take factorial n common from both of them. Here you are left with 1 by, because this one is r factorial, I am going to write it r multiply r minus 1 factorial. Can you? I am writing r factorial as r into r minus 1 factorial. Why this one is done? Because the second denominator consists one r minus 1 factorial. To take LCM, we are making the term having factorial same. This n minus r factorial as it is. By this similar concept, n factorial have been taken common, you are left with 1 here, r minus 1 factorial as it is, because here also n r minus 1 factorial, and this is going to be broken. This can be written as n minus r plus 1 into n minus r factorial. Can you? Of course, because if needed, 10's factorial can be written as 10 multiply 9 factorial. Same thing has been done here. This one's factorial is this one multiply this one minus 1 factorial. N factorial as it is, let us take LCM. LCM will be r into r minus 1 factorial and even n minus r plus 1 into n minus r factorial. We have taken LCM, here r minus 1 factorial, here n minus r factorial. The terms having factorial are same in both the denominators, that is why it has become easy to take LCM. Here you are left with r, and here left with n minus r plus 1. Simplify it, everything is here other than this one, this term 1, so this term will come here, n minus r plus 1. Here everything is there except r, so r will come here. R n minus r will cancel. Now you are left with, this one is n plus 1 and this n factorial afterwards, by r into r minus 1 factorial as it is, even n minus r plus 1 into n minus r factorial as it is. Can you write n plus 1 into n factorial as n plus 1 factorial? Of course, because if 10's factorial can be written as 10 into 9 factorial, then 10 into 9 factorial can be also written as 10's factorial. That is done here. 10 into 10 plus 1 factorial is here. That is why this can be written as n plus 1 factorial. By the same logic, this r into r minus 1 factorial can be again written as r factorial, and this n minus r plus 1 into n minus r factorial can be written as n minus r plus 1 factorial. Now you can say, is it c n plus 1 comma r? Let us check. See, first comma second, first factorial, second factorial, first minus second factorial. So this expression can be written as Cn plus 1 comma r, which is our RHS. And this rule 1 is called the Pascal's rule of combination.